there guys, how's it going? Mike coming back at you here with another video on vector calculus. In the previous video, we thought we were going to do a follow-up on Stokes' theorem, but we didn't. We partied because it's my birthday. In this video, we're going to talk about the divergence theorem. We're going to talk about the background of this theorem. We're going to talk about the statement of it, and we're also going to get into the proof of this theorem. Now, just like going through the proof of Stokes' theorem, I'm not going to expect you to regurgitate this proof back at me, but you should be able to follow along with this proof, and you should be able to understand why we're doing what it is that we are doing. So before we state the divergence theorem, we have to talk about a key aspect of this theorem, and specifically the hypotheses of this theorem, which pertain to elementary regions. What the heck is an elementary region? If you have some region W, that's a subset of R3, it's an elementary region if it can be defined by restricting one variable to be bounded by two functions of the other two variables. And these two functions have to be such that the domains of these two functions have to be an elementary region in the plane. Now, again, elementary region in the plane now, what the heck are we talking about here? When we talk about an elementary region in the plane, we mean a region that has no holes, no gaps, is not broken up into two separate chunks, it's all connected with each other. Here's an example of an elementary region. The unit ball, the sphere of radius 1 centered at the origin. You can take the z and write z to be bounded between two functions, each of them a function of x and y. I call the lower bounding function g1 and the upper bounding function g2. G1 specifically is minus the square root of 1 minus x squared minus y squared, and G2 is positive square root of 1 minus x squared minus y squared. And each of these functions contains the common domain D, which is the circle of radius 1 centered at the origin. And as we know, this is a nice region. There's no holes, there's no gaps, it's not broken up into two pieces, and it's all connected. So this is an example of an elementary region in the plane, and thus the unit ball B is an example of an elementary region in R3. Now, the unit ball, as well as many other regions, can also be represented by taking any variable, x and y as well, and having each of these guys be bounded by functions of the other two variables. I could take that same sphere of radius 1, and I can rewrite it so that x is bounded between two functions, alpha 1 and alpha 2, each of these guys being functions of y and z. And I could also take the y variable, and I could make it so that y is bounded between two functions, beta 1 and beta 2, each of these functions being a function of x and z. And whether you have the x's bounded by alphas or the y's bounded by betas, you have a common domain between these bounding functions that are elementary regions in the yz and xz planes, respectively. So when you have this flexibility, when you can take any variable, x, y, or z, and make one of them be bounded by two functions of the other two variables, and these two bounding functions have a common domain that is a nice connected region with no holes, no gaps, it's not broken up, then your region in R3, W, we say that it's a symmetric elementary region. And this is very important to the divergence theorem, and this is why I went into so much detail going into all these possible cases. Because when we go through the proof of this theorem, we're going to see how the flexibility to bound one variable between functions in terms of the others comes in to proving this theorem to be true. So now Here's the actual statement of our theorem. Let W, which is a subset of R3, be a symmetric elementary region, and let partial W be the oriented closed surface that bounds W. So W is everything on the inside of that outer layer that's closing in our region. Partial W is just that outer layer. It's that outer surface. Let capital F hat be a vector field whose first partial derivatives are continuous. Then for the outward unit normal n hat, the double integral over partial W of f hat dot d capital S hat equals the double integral over partial W of f hat dot n hat d capital S. Those two things are just two ways to write the same thing. Those are equal to the triple integral over W of the divergence of f hat dv. So this is the statement of the divergence theorem. Next, we're going to go into the actual proof of it. And as I said before, you should be able to follow along with what's going on here. Not necessarily something you have to spit back out at me, but you should be able to understand what's going on here. So we have our vector field, capital F hat, P, Q, and R, each of these guys functions of x, y, and z. The divergence of this vector field, pretty straightforward, P sub x plus Q sub y plus R sub z. So if we make that substitution, and then we multiply the dv into each of those three terms, and then we break the triple integral up at the plus signs, we see that that right-hand triple integral that we have here turns into the triple integral over w of p sub x dv plus triple integral over w of q sub y dv plus triple integral over w of r sub z dv. Now, we're going to work with the surface integral that we have in the middle here. Namely, we're going to work with this guy. If I make the substitution for f hat, p times I hat, plus q times j hat, plus r times k hat, and then I take the dot product of that whole thing with n hat, and I break up the double integral at the plus signs, I get the sum of three double integrals. Double integral over partial w of p times I hat dot n hat ds, plus double integral over partial w of q times j hat dot n hat d capital S, plus double integral over partial w of r times k hat dot n hat d capital S. All those guys are d capital S's. So the triple integral broke up into the sum of 3. The double integral broke up into the sum of 3. So if we can show that corresponding triple and double integrals are equal, then our proof is complete. So we want to show that each of these three equations holds. Now we're only going to prove one of these because the other two hold by a similar method and a similar argument. So we're not going to go through all three of these. But we are going to work with the third one here. We're going to show that the triple integral over w of r sub z dv is equal to the double integral over partial w of r times k hat dot n hat d capital S. So, since our region W is a symmetric elementary region, as we assumed in the hypotheses, I can take that z variable and I can have z bounded between two functions, g1 and g2, and each of these functions are functions of x and y. These functions have a common domain D. So making that substitution into, or these substitutions, I should say, into the triple integral, the triple integral over w becomes the double integral over d of the integral from g1 to g2 of r sub z. And the g1 and g2 are the z bounds, so we have to have a dz following right after that r sub z. And then on the outside, we have the dx and dy associated with our domain capital D. We could have put dy dx. It really doesn't matter, but this is just what we chose to do. So if I take r sub z and I integrate it with respect to z, that's just going to get me back to whatever r was, r of x, y, z. But now take your top bound, plug it in for z, take your bottom bound, plug it in for z, take the difference, and you're left with this guy right here. So all we did for this half of it is we just made some basic substitutions for the bounds for our region W, and then we did one of our three iterated integrals here. Now we're going to work with the other side of it. Now we're going to work with this guy right here. Now, the boundary, partial W, could, in the worst possible case, consist of the bottom surface, S1. That's your surface here. That's bounded on two sides by solid black lines and on the other two sides by dashed black lines. This bottom surface has some equation, g1 of x comma y. The top surface, S2, has some equation, g sub 2. And on the sides, if your 3D region W has any sides to it, it may be the case that there's no sides to it, or there's maybe only one side or two sides or three sides to it. Who knows? But if there are any sides to it, then we'll call these surfaces S3, S4, S5, and S6. We're not going to say that there are particular functions bounding these sides, because we're going to see very shortly that if there's any functions forming these sides, they don't matter. If we look at these side surfaces, and we look at the outward pointing unit normal. So that's there, that's going out there, and then picture normal vectors going out that way, and then we'll go out that way as well. Each of these normal vectors for these surfaces, S3, S4, S5, and S6, each of those guys are pointing in a direction that is perpendicular to k hat. These guys are pointing parallel to the xy plane. And we know that if we take the dot product of two vectors that are perpendicular, we're just going to get 0. So the double integral over the entire boundary of r times k hat dot n hat ds is equal to the sum of the double integral over each of the individual surfaces making up our entire boundary of r times k hat dot n hat d capital S. But this last piece here, for each of these guys here, k hat dot n hat equals 0. So all those guys just get wiped out, and we're only left with the double integral over the bottom surface of that stuff plus the double integral over the top surface of that stuff. So let's look at S1. For S1, the outward unit normal is going to point downward. When we talked about what is our n hat d capital S going to be, for the upward, it was minus g sub x, comma, minus g sub y, comma, positive 1. So to get it pointing downward, we multiply every component by negative 1. So we have a positive g sub x, a positive g sub y, and a negative 1. So this right here, as we said, is n hat dot d capital S. So if I make this substitution into the first integral that we have right here, this is going to get us minus r of x comma y comma g sub 1. We're only concerned with the k component of ds hat, and that k component is -1. For the surface S2, the outward unit normal is the upward pointing unit normal. This is what we're used to. So we find that ds hat is going to be minus g sub x minus g sub y comma +1. And when you make this substitution in, we're only looking at the k component, or the third component of this vector. So we're looking at r times 1, or r of x comma y comma g sub 2. So taking these results that we found, the double integral over the entire boundary of r times k hat dot n hat ds, d capital S that is, which was the sum of these two double integrals. When you make those substitutions, you get the double integral over d of r of x comma y comma g sub 2 minus r of x comma y comma g sub 1. And we saw that this is identically the same thing as triangle that we had here. So this right here shows that these two things right here are indeed the same. And showing these two equations right here, the first two equations, comes down to that same thing. I can take, if I look at the second equation that we have here, I can take y. I can have the y's being bounded by two functions, each one a function of x and z. I can make the substitutions for bounds into my triple integral, get that down to one thing. If I look at the surface, if I look at the boundary of my region, which is my surface, any side faces, if you will, of my boundary surface are going to be perpendicular to the vector j hat. So what's only in the only the surfaces that have a negative or positive normal in the y direction, we're only going to work with those surfaces, and you come out to get the same thing as you did in the triple integral. So that is the proof of the divergence theorem here. Now, let's go back to the statement of the divergence theorem, and let's see what exactly we have going on here. The two integrals, the first two, double integral over partial w of f hat dot n hat d capital S, those right there are saying the same thing. And what it's saying is that right there is the outward flux of our vector field f hat across the boundary of this surface here. F hat dot n hat, this is the normal component of our vector field. We're taking the integral over the boundary of our surface of the normal component of our vector field. And the triple integral on the right, we're taking the triple integral of the divergence of our vector field f hat over the interior of that boundary surface, over the inside of what's inside our boundary surface. So if we just think about those two things, the integral of the normal component of our vector field over the boundary, this is also the flux of our vector field across our boundary, is equal to the integral of the divergence of our vector field over the interior of our boundary. Well, if we think back to talking about Green's theorem, we talked about the flux divergence form of Green's theorem, which said that the integral over the boundary of some region D of p dy minus q dx, which was our integral for flux, the flux of our vector field across that boundary curve, is equal to the double integral over d of p sub x plus q sub y, dy dx. And we said that p sub x plus q sub y was the divergence of our two-dimensional vector field. Well, these two things sound like they are the same thing, and if you're thinking that, you are exactly correct. These things are the exact same thing. And this leads to another big connection that we want to draw between the theorems that we're learning about in this course. The flux divergence theorem, the flux divergence form of Green's theorem, if you scale it up one dimension into R3, gives you the divergence theorem. These two theorems are saying the exact same thing. They're saying that the flux of your vector field across the boundary of your region is equal to the integral of the divergence of your vector field over the interior of your region. So this is a big result that we want to keep in mind, and we want to know that exists between these two theorems. So this video concludes the background on the divergence theorem, the statement of it, the proof of it, and then what is this thing saying relative to other theorems we have learned in this course. In the next video, we are going to go through several sample problems to see how we use the divergence theorem. If you have any questions or comments, be sure to drop them in the comment section below. Otherwise, until the next video, take it easy.